Hello, this video is called Just Enough C to have fun with. It's not called Just Enough C to be a professional C programmer because you're not going to learn that much. And it's also not called Just Enough C to be dangerous because you absolutely should not be doing anything critical with the knowledge you get in this video. However, if you want to play around with C, have fun and learn a bit more about computers, then this is the video for you. We're going to start off talking about compilation, and I'm also going to give you a project template that you can use to get started. Next, we're going to take a really fast run through all of the key syntax. That's going to take about 10 minutes and it's going to be really pacey. Then after that, we're going to talk about the thing that makes C particularly fun and also a little bit unapproachable, which is how it handles memory, how you deal with types like arrays and strings. Finally, I'm going to give you some exercises to go away with, including fizzbuzz, a prime sieve, and a number to word converter, as well as something for members as well. Let's get into it. All right. Title card 1. So here I'm going to show you how to take C code and convert it into a running executable. It shouldn't take too long. So C is what's known as a compiled language, and this is commonly opposed to an interpreted language. The difference is, in an interpreted language like Python, you have a program called Python whose job it is to take the code and run it. Whereas in a compiled language like C, you have a program called a compiler whose job it is to take the code and then compile it down into a machine code format, which can then run on the computer directly. So you end up with essentially a binary executable file, which is the thing that runs. So practically, if you want to run Python, you need the code in the Python interpreter called Python on the command line, whereas in C, you need a compiler to compile the code into an executable, and then that executable can run by itself. Let's see it in action. So I've got a file here called hello.c, and I'm going to use the compiler clang or clang to compile it down into a file called executable. You can call these whatever you want. Then now I've done this, I can go ahead and run my executable, and after a short delay while macOS works out whether it's trusted, we then can see the output of the code. Now clang is the common compiler you're going to see on Macs. There is another compiler called GCC, which you might see more often on Linux. Both are on both platforms. If you run GCC on your Mac, you'll find out it does actually exist, but actually it's just a link to the Clang compiler. You can use GCC if you want, though, you just need to install it. And just for fun, there is a third option called CC, which probably is going to link to wherever the C compiler is on your computer. If your computer's set up for development, you're probably going to have a C compiler on it anyway, but there are ways of installing them which you can look into if you need to. Now, Clang and GCC have a bunch of different options. I'm going to go through the most common ones you're going to want to pay attention to while you're playing around with C. You're often going to see the capital O flag, and this indicates how optimized the compiler should make the executable. Optimization is the process that the compiler might go through to make the code run more efficiently, either in speed or in memory. 3 is typically the highest level, and 0 is typically the least. At this point, because we're playing around with C and we want to see what it compiles into, I've been keeping it at 0, disabling essentially all of the optimizations. But if you want to turn it up and see how fast it goes, then 3 is your number. I've also been compiling with the G option, which makes debugging easier by also outputting what's called symbols, which enable us to tie back bits of the executable to bits of the code. Finally, C compilers will also support having warnings enabled, and the common thing you want to see here is capital W all, which is going to enable all the warnings and give you the maximum insight into any mistakes you might be making. The lowercase 0, as we've seen, decides the file name of the output executable. If you don't put anything in here, you're going to get a.out as the output file name. Worth noting here that C compilers don't always produce executables. They can produce object files which are not directly executable, so that later they can be bundled together with other object files and produce an executable in the end. We're keeping it simple here, so we're just outputting executables, but just worth you knowing. And finally, we've got the input file, the code file itself. You can sometimes see multiple of these here, but we're just going to use one. You can run the executable with the familiar --dash syntax. And all of those options work roughly the same with GCC too. So that's how you compile and run C code. I've also produced a little project template specifically designed for toy projects, which I'm going to show you now. It just gives you a little bit of structure for your code and also automates some of the more common commands. I'll put a link to these instructions on the OODS website, but all we're doing here is cloning a repository without then including the Git part of it. The README has a few instructions. It also includes some tools to help check everything's sorted and installed properly. It contains a little thing to run some code. You probably wouldn't use this in a normal makefile. Oh, and by the way, makefile is to do with building. It's essentially a way that C programmers use to automate the building of complex projects. And since our project's pretty simple, I've used it here mostly to automate a few commands. The template is made up of 3 main C files. The first is main.c, which is what gets run when we run make run. The second is lib.c, which is where your implementation code should mostly go. So main should mostly be about printing things out and getting user input and all that sort of stuff. And then lib.c is where the implementation function should go. So the stuff you might unit test in a real application. And speaking of unit tests, I've included a very small no library testing system as well. It's designed for testing the implementation functions in lib.c. Don't try and test main.c at this point. It's going to get you into a real mess. Instead, it can be a useful way to run bits of lib.c if you want to try out some other functions and take a more test-driven approach. This file is made up of a few parts. It includes a bunch of stuff at the top, which is going to be useful for the tests. It then sets up some of what's called macros, and macros are essentially like built-in find and replace in C. So you can see I've got this macro here called test brackets name, and that means that whenever we use this macro down here, it's going to get replaced by this code. Don't worry too much about these. You should be able to follow the pattern if you look at the test down below. And indeed, down below, we see this test for the addition function, and we're using asserts with comparison operator. So this is going to pass the test if we get true or fail the test if we get false. So I'll show you this now. It also does some nice colors. Always nice to see the colors. Now, because there's no operator for string comparison in C, I've also included an assertion macro that works with comparing strings using something called strcomp. And finally, there's a main function where you run each block of tests. So a fairly simple testing system if you want to write, say, a C function that does something cool, and then you can use this testing file to actually assert that it does what you want it to without having to produce a really messy main file. Little tip, if it helps you code, I always hate rerunning things, especially in videos. So I've installed the tool Watch, which you should have available on Brew if you're on a Mac. And this will enable me to keep an eye on commands as I'm editing the code. So this way I'm using Watch. It's going to refresh every half second. It's going to get rid of the title, which is just noise for me. And it's also going to allow us to have color in there as well. And now as I edit the tests, I'm able to see them respond, which is pretty nice. If you want to use this template, there's a link directly in the description, as well as on the ODE's website. And now we're going to go and look at some C syntax. Firstly, we're going to talk about includes. Now, C's standard library, unlike other languages, is not built into the language itself, so you need to include the parts of it you want to use. This is known as system libraries, and we've got 2 examples here surrounded by the angle brackets, which means we're including a system library, not some file we've got hanging around. The 2 we've got are stdio.h, standard input and output.h, and string.h, which is functions to do with strings. After this, we've got an include for a file that we have written, and you can see it's surrounded by quotes, not angle brackets. What happens when you include a file like this in C? It just gets inlined straight into the file, and everything in the other C file gets chunked into the C file we're including from. Now, do note that including C files directly is not considered best practice in a professional project. Typically, you would write a header file that says what you want to expose from your C file, and then you would include that and then link in the compiled C file directly. We're not going to do that because we're trying to keep it simple. Now we're going to look at functions. Functions in C are described in a fairly familiar way. You've got a return type on the start. In this case, it's int for integer. We've got the function name, in this case mul, and then we've got 2 parameters, int a and int b, both integers. We've then got a block which has got the code in it. Looking inside the code, we can see that we have a list of statements. Statements in C end with a semicolon. So we have our variable assignment, and then we've got a return statement. Just as you'd expect, any lines after the return statement will not be executed, and the value after the return keyword will be returned. Also worth noting that recursion is available in C, so you can use that freely, subject to the normal rules around tail recursion and such like. If you don't know about that, don't worry about it. One area where C differs from other languages, you cannot return arrays directly, and anything like arrays, which includes strings. So you can't return strings from a function, and you can't return arrays from a function. Most of the time you're going to return numeric values like integers or pointers or things like that. There are other things you can return, but we're not going to touch on those right now. Now, how do you get around the limitation on returning strings and returning arrays? I'm going to get into that later in the video. For printing in C, you're going to typically use two functions. The first is puts, put string, which is just going to put out a string into the terminal. It has a new line at the end, and you cannot interpolate. No string interpolation available. If you want string interpolation, you're going to need to use printf. Printf takes as its first argument the format string, which is just a string with normal stringy stuff in it, but also with 0 or more format specifiers. These are like placeholders, and they need to include the type of data that you want to print out, and the one you use may affect how the data you're giving it will be printed out as well. After this, in however many extra arguments there are the values you want to put in to each format specifier. If you use prepared statements or anything like that in an ORM or SQL, it's a bit like that. You provide the placeholders in the string, and then you pass in those placeholders as the arguments following. Here's a short list of format specifiers. There are way more if you want to look them up. Loops in C work roughly like you'd expect. We've got a while loop which runs until the condition evaluates to false, and we've got a for loop which I always forget the meaning of. Basically, you've got a setup statement, you've got a while loop style condition, and then you've got your increment on the end. So here we start off with I equals 0, and then while I is less than 100, we increment up 7 each time. We then run that block until that condition evaluates to false, just like the while loop. Another thing worth noting is we've got break and continue, and they operate just like in other languages. Break will break out of the loop, so no more iterations, and continue will jump ahead to the next iteration. I've started imagining it as a sandwich with the while loop condition as the filling and the bread being the increment and the step. Maybe that'll help me remember at least. Conditionals again, they work roughly like you'd expect. We've got ifs, else, the usual stuff. We've also got a reasonably full complement of logical operators and comparison operators. So we've got double ampersand for and, we've got double pipe for or. If you get these wrong, you'll be using bitwise arithmetic, which you don't want, unless you do want it, in which case use those. We've also got double equals, not equals, less than, all the usual stuff. While we're on the topic of operators, the one that always annoys me is the power operator. Fortunately in C, there is no power operator. There's a function in math which you can use if you want, but there's no operator for it, so nothing to worry about. Data types in C work slightly differently to other languages. First thing to note is there's fewer of them, there's no built-in fancy stuff. Second to note is the ones that you might normally have one of, like number, there's actually quite a few. And they differ by size in bytes and therefore what numbers they can represent. So if you have an integer, we could also have an unsigned integer that lets us go higher, but at the cost of negative numbers. You could have unsigned longs, long longs, there's many different kinds. There's also floating point numbers, characters which operate a bit like numbers, but we look at them like letters. We've also got size t, and I'm including size t because while you might not use it to play around with, if you're looking at other people's C code, you're likely to see it. Size t essentially means give me a type that is big enough to hold the size of or the address of any object that could fit in memory on this machine. So it's quite useful when you're dealing with memory addresses, size of data structures you're not quite sure you know the size of, stuff like that. So you see it quite a lot in systems code. Now moving on to arrays. Arrays in C are a little more basic than you might be useful. For starters, they're not lists. If you don't know what that means, don't worry about it right now, but it means that we don't have built-in things like length or reverse or anything sort of fancy like that. All C's arrays are a certain area of memory that has been cleared for you to put a certain number of a certain data type in. So the actual length of the array will differ depending on how many items you've decided to allocate and what the type of those items is. Also worth noting that C arrays are essentially fixed in size. So if you want to have an array that changes in length over the time that you're running your program, you're going to have to do some extra work to make that happen. Now defining C arrays is also interesting. Now you might expect arrays in C to be defined like this, where you have an array of integers type and then the name is numbers 1 without any extra gubbins on it. But in fact, C arrays are defined with this syntax. The type of the element goes first, then the name of the variable, and then the size of the array within the square brackets. On this particular line, we've declared the array, which means the memory has been allocated, but we haven't put any data into it. Now note what this is going to mean is that it's going to be filled with junk values. If you're very lucky, those junk values will all be 0. Most likely, they're not going to be. They're going to be full of other stuff. So typically essential to initialize your array with some data. On the next line, you can see we've got an array numbers 2. Now I haven't specified the size here, but the compiler knows the size because I've given it a fixed list of items to put in memory. So the size here is still fixed. Now strings in C are also arrays. They're arrays of characters. You can see here I've got a string of length 6, and I've actually put the string hello into it, which those fast counters here will know is 5 characters long, not 6. The reason it has to be 6 is because strings in C are what's known as null terminated. They have to end with a byte which is exactly 0. That's what tells C that the string is done. This is kind of useful in some ways. Also, it can get you into trouble if you forget to put it on, because anything that works with strings may then go and read on off the end of the string and encounter all kinds of other data. This can be a source of security issues if an attacker has managed to control that data in some other way. So just worth remembering, strings always have to end in a null byte. Now we could talk loads about how arrays and strings behave in C. It's one of the really interesting parts of C, but we're not going to do that right now. We're going to do that later. Let's move on. Do you like classes, objects? Well, bad news. C doesn't have either of those things. Instead, C has something called structs. And structs are a little bit like a database record, or if you've ever used objects in C a bit like a record, it's a bit like that. What we have here is a struct person, which has 2 properties, let's say, name and height. They must be defined with their types and lengths up front, and then you can create structs with the code struct, then the name of the struct, name of the variable, and then equals, and then these braces here with values. You can pass them in as an ordered list, essentially, or you can pass them in by name like this. Then when you want to get data out, there's a familiar dot syntax you might be used to from basically any other language you've come across. And rounding up our syntax roundup, we've got the main function. Now, if you were to compile this file called main.c as an executable, the main function will be the one to execute. We don't have to call the file main.c, it could be anything, but what matters is if we compile this as an executable, the main function gets executed. It can take no arguments or it can take 2 arguments. The first argument being argc, which is the count of arguments that this has been given, say on the command line, and the second is an array of strings or an array of arrays of characters, which is the actual arguments themselves. The value returned from the main function is the exit code, which should be 0 if the command succeeds, and anything else to be defined by the programmer if it fails. And that's it. That's all the C syntax I'm going to show you. Let's move on to talking about some of the semantics of the syntax. My handwriting is really not good. So now we're going to look at the conundrum of how do you return a string or an array from a C function. And for that, we're going to have to look at how memory works in a C program. We're going to look at 3 different examples. The first one is not going to work, not a viable solution, but it's the one you might jump to if you're used to higher level languages. The second one involves buffers, and the third one involves allocating memory on the heap. I'll explain all that when we get there. Let's look at the first example. So the function we're going to look at, which is called myStrcat, my string concatenate, is a function that just takes 2 strings and then returns the strings concatenated together, a fairly simple function. For each example, I'm going to show you the call, the function itself, and then some of the areas of memory that are involved in the running of these programs. Now, as I said, this one is not going to work, and you can see already some syntax errors popping up. Now, going through the call first, you can see that we're declaring a variable called result, which is an array of characters, so a string. We're then calling the myStrcat function, which takes 2 strings, hi and ya, and then we're asserting using a little macro that I've written that the result is equal to the string higher. Then, if we jump across to the function, we can see that things are not quite right. We've got a few red lines underneath indicating some syntax errors. Still, let's ignore those for now and move on to how we'd like this function to work. It takes 2 arguments, the strings a and b, and it also returns a string. It then sets up a string with 5 spaces in it. How do we know 5? Well, we don't really, but we'll skip over that for now. We use the function sprintf, which is a bit like printf, but instead of printing to the terminal so we can see it, it prints to a string buffer. So we've got a buffer string here, and sprintf is going to put the result of formatting these 2 strings next to each other into that string. So it works a bit like string concatenation. And then we return the buffer string, and in theory it comes out here into the result string. Now this isn't going to work for a number of reasons, but let's start with all these red underlines. What we're being told here is that functions in C cannot return strings, and it's actually built into the syntax in a pretty deep way. For starters, this, while it looks like a type like you might see in TypeScript, it's not actually a type in C, because actually when you declare an array in C, these brackets don't go next to the type, they go next to the variable name instead. So this already doesn't make much sense. We could try moving it to here, but that's not going to work either. Now there is a version of this function that will not work, but it will syntactically work. So I'll show you that. Now this version is different in that we're not passing around array types anymore. Instead, we're passing around pointers as indicated with these little asterisks here. So these are now pointers to strings rather than strings or arrays themselves. Just another bit on pointers here. A pointer is a special kind of variable in C which contains the address to another place in memory which we can use reasonably transparently to edit and access that area in memory. So here we have a variable myPtr, which is a pointer, which is then assigned the address of myStr, and then we can use it to access and edit that memory. So just imagine pointers as a reference to another area in memory which we can use reasonably transparently. This does actually run, and it does sort of work, so I'm going to talk you through what happens when we run this. So at the start of the program, we have some values in memory, and these are these values here, high, yar, and higher. These are stored in the data section of the program, and I've indicated them with these little boxes here. You can see they each have an address. So the string high starts at the address 0010, and the string yar starts at 0018, because you can see that it's in column 8 and in row 0010. The string high is also in there, which is what we're going to use for comparison. So this is the situation at the start of our program. So in this line, we set up an area of memory, which we're going to call result, which is supposed to hold a pointer, which is an address to an area of memory, which points to an array of characters. So I'm going to indicate this as starting, let's say, here in the area of memory known as the stack, which is for local variables. And the address of this result pointer is going to be 0102. In this bit of memory is going to go the address to the string which was returned by myStirCat. But we don't have that address yet, so we're just going to set it up, and then we're not going to fill it yet. At this point, we call the function myStirCat, and our execution jumps over to the start of that function. Because we've jumped over to another function, we now have another area in memory that we're going to put our local variables for this function. And I'm going to say that starts from 0110. We have some arguments to store, star A and star B, which are also pointers, and they are pointers to the areas of memory that contain the strings high and yar. So I'll put those in now. Now, since we do know where those strings are located in memory, I've put in the addresses, which are 0010 and 0018. And those are now stored in these variables A and B, sometimes notated as star A and star B because they're pointers, which means that when we try to access them, instead of getting the contents of that variable, which is 10 and 18 in hex, we're going to go through to the piece of memory that that pointer is pointing to. This is sometimes known as dereferencing a pointer. Now moving down in our function, we're going to declare this buffer variable which needs 5 spaces. Just to make it a little easier to see, I'm going to put this on the next line. The computer may or may not actually do that, but this is simplifying a bunch of stuff, so bear with me for now. Now this buffer is not being declared as a pointer, so it's going to go in the stack area of memory, its actual contents, not just an address to another area of memory where the contents is. We'll fill it up with zeros and we move on to the next line. At this point, we will call sprintf, which will then copy in the data from A and B and then put a null byte on the end as well. And then we'll move on down a line to return the buffer. Now, here's where things start to go wrong. C functions cannot return arrays. So what this C function is going to do, since it's declared as returning a pointer, it's going to return a pointer to the area of memory that buffer corresponds to. So it's going to return essentially 0120 as a memory location. This means that the result pointer in our original call is going to be filled in with that memory address. And then when we move on to the next line and compare result against the string higher, which is in the data section, we're going to find that they are the same and the test or the assertion will pass. And it looks roughly like this. There are some warnings, but they're only warnings, right? So don't worry about it. So this works just about, but it's going to stop working really soon. I'm going to show you another example which does something in between calling myStirCat and testing it. So here we've got a new version of the function which calls myStirCat, then uses printf to print out some information for us to see, and then actually compares it. What we notice then is not only does our assertion start failing, but also when we print out result, we get a bunch of nonsense rather than what we're expecting, which is super weird. To show you what's going on, I'm going to rewind it a little bit to just after we have called myStirCat and we then start calling printf. And I'm also going to break up for you the memory that is part of the test and the memory that is part of our myStirCat function. So in this example, we're showing that 0x0100 is the memory for our test, and when we call the function myStirCat, it gets given the next 3 lines of memory. Now the thing that breaks is when you return from a C function and it's no longer executing, all of its local variables are essentially marked as no longer used. They're ready to be used by other functions that might be called. So when we call printf, that area of memory is going to get reused for whatever local variables printf wants to use. And so it's going to get full of other stuff. And so our pointer to buffer is going to point to a random bit of memory that could be used for literally anything, not our data, which is why when we run it, we get junk out now, given that we've called another function in the meantime. And here's an example of what that might actually look like. So this approach is not going to work. And the core reason it's not going to work is the same reason you can't return arrays from C functions. When you call a function in C, all of the memory and data that it sets up is going to be marked as invalid after it's done. The only thing you get to keep is the return value, and the return value cannot be an array. And also, if you return a pointer to an array, there's no guarantee that that memory is going to be preserved magically just because you'd like it to. So we need to find another way to do this. And here is one solution to this problem. Instead of asking the C function to return a new string, we create a string before we call the function, give our function the address to that string. That function can then modify that string in place, and then we can use the string back in our calling code. So I'll talk you through now how this works. First, we set up a variable called result, which is going to be a string of 5 characters long, initially filled with zeros, and I'm going to reflect that in the stack memory too. Next, we call that function with that string, which we're going to call buffer, as well as the 2 strings that we want to join together. This then passes control to our function. And before I set up the memory for this function, I'm going to do a little swap on you. Now, C has something called array pointer decay, which means that when strings are passed in to functions, they actually get replaced by pointers. So this code here with all of the square brackets in is kind of syntactic sugar for a different piece of code that uses pointers instead. So I'm going to swap that out and then I'm going to show you how it plays out in memory. So see here how instead of the square brackets, we've got pointers. It's the same sort of deal. Instead of passing strings in directly, we're passing in pointers to strings. Now to flow it out in memory as 3 pointers to 3 different strings. So our function now has a pointer to buffer, which is 0100, a pointer to A, which is 0010, and a pointer to B, which is 0018, all in hex, of course. Now our function calls sprintf, which is going to populate the memory that the buffer pointer is pointing to with the memory that A is pointing to and the memory that B is pointing to. This function does not return anything, that's what we mean by void, so the function just concludes and passes control back to the caller. At this point, the memory associated with our function is invalidated, but it's not a problem because that memory only contains pointers to the memory we really care about. So we can just throw it away and it can get reused for other things. Our caller still has access to the memory it cares about, which is the memory that holds the result string. So as a result, when it comes to our assertion, we can test our string in the stack memory against the string in the data section perfectly fine, and this data will stick around as long as our function does, so we don't need to worry about calling any other functions and causing problems. This approach of passing in a buffer for a function to then do its work with is actually really common, and you'll see it a lot in the C system libraries. It's probably the favored approach for doing things like this, but there is something which is a bit suboptimal about our particular version of this, and I'm going to show you what it is. So let's say that we pass in a string that was too long, that couldn't fit in a 5-character buffer. Our execution would jump over to the other function as normal. Sprintf would actually do something really weird. It would write over the end of the buffer, and as a result, it would start writing into other variables, including the variables in our function. So the pointer to buffer is now no longer right. This wouldn't actually break our program in this case, but you can see how this is really not a good outcome. It's called a buffer overflow, and it's a situation where a buffer has been overflown by a function being tricked or mistaken into writing data off of the end of the memory that is allocated for a particular string or array. And it can cause all kinds of big problems, including security problems, if an attacker manages to use this to alter the code that is going to run next. So we have techniques to defend against this, which I'm going to show you now. Now here I've replaced sprintf with snrprintf or snprintf, string printf with an n in it, so it means only for a number of times. snprintf takes an additional argument, which is the length of the buffer, which is the maximum length of characters that snprintf is going to write to that buffer. As a result, we then need to pass in a new argument, which I've set to be type size t, since it's a size, and I've called it bufflen, the length of the buffer. And here's how we call it. We pass in the number 5, which is the length of the buffer, or we could pass in size of result, which would do the same thing. Now when snprintf runs, it's just going to stop. It's not going to write over the end of the buffer. It also returns some important values, including a minus number of things don't go quite to plan, and also the number of bytes that it would have written if it had succeeded writing. So all this is very useful to keep track of if you're going to write to the same buffer multiple times, so you can keep track of how much buffer is left. So that's really the main solution to how you solve this problem. It has a lot of advantages over the other approach I'm going to show you second, but the other approach is sort of interesting as well, so let's take a look at it. So in this approach, we allocate some memory in a new place in memory we've not looked at called the heap. We'll look into this further in a future edition of Odes, but suffice to say for now, you've got the data section, which stores things that are literals in the code. You've got the stack memory, which is kind of tied to the function that's executing, and the stack as you go forward and back of functions that are being called, and the heap, which is memory that's kind of outside of that, located in a different place. The heap is also useful because you can quite easily resize data that lives in the heap. So if you have a string and then you want to create a bigger string later, then you can use the heap for that. I'll run you through how this code executes and plays out in memory. So first we declare a pointer to a string, which we're going to call result. It's not got any data in it yet, it's just empty. Next we call myStircat, and execution flips over to there. Note in the function signature, myStircat now returns a pointer, that's what that asterisk means, and it takes 2 strings as arguments. And remember that while they've got the square brackets there, these are just pointers. Moving on to the next line, you can see a new function called malloc, one of the most famous functions, I think. It stands for memory allocate, and we give it 1 argument, which is the length of memory in bytes that we want to allocate. And we calculate this by getting the length of string A, the length of string B, plus 1 for the null byte, and then multiplying by the size of the character type, which is 1 byte, although if it was a different type, it might be something else. Malloc comes from the system library stdlib.h, and strlen comes from the string system library. I'll show you how this plays out in memory. Malloc then returns a pointer to a new area of memory that has been allocated in this heap area. We can then move down into the next line, and sprintf will then take the data at A and B, and it will copy it into the point of memory in the heap that has been allocated to result. And handily, in this example, we've already determined the length of these strings, so we don't need to worry about buffer overflow. Finally, we return a pointer to result to our caller. This is then put inside the result pointer variable in our caller. And of course, the memory associated with our function is invalidated. But it doesn't matter because our string is in the area of memory in the heap and that memory sticks around. This means that we can then assert, we can call whatever functions we want and the function works as we expect. Now, because we're working in C, of course, there is a catch, which possibly is what C stands for. Take a look at this code, take a think about what I've just talked you through and see if you can see what the problem might be. Did you get it? The problem is that we have allocated some memory in this area called the heap, and nobody is ever going to clean that up. It's going to be allocated until the end of our program and the whole thing is torn down. So if our program is going to run a long time, let's say it's a web server or something else, then this memory is going to build up and build up every time that my stircat is called. It's going to keep allocating new memory, and eventually that'll absorb all of the memory on the machine, which is not very good because the machine needs memory to operate and do other things. So malloc has a corresponding function called free, which frees up the memory when we're no longer using it. And it's our responsibility as the programmer to call free when we're done with a piece of memory allocated on the heap. This then poses a question. Where do we call free? We can't call it inside my stircat because our caller is going to need to use that area of memory in order to get the result. So my stircat is unable to call free. It wouldn't make sense for it to call free. So we actually have to call free in the caller, which means that we have to know this. We have to know that my stircat is going to call malloc and then know and remember to call free afterwards when we're done with that variable. This is a big cause of what's called memory leaks, and they can be quite subtle, hard to find, hard to diagnose, and really hard to remember. When you're coding all day, you're likely to make mistakes like this on a regular basis. So there's lots of tooling that's designed to help people avoid making these mistakes. I would say, though, the best approach is not to do this in the first place unless you absolutely need to. If we look back at our buffer solution, we can realize we don't actually have that problem at all. With the buffer solution, because our caller is responsible for creating the buffer, they're either going to do it on the stack, in which case it's going to be freed anyway when that function returns, or if they do need to use malloc to allocate some memory on the heap, they're then going to know that it's their responsibility to free it. So it's actually better in a lot of ways. It takes advantage of the natural approach of freeing memory from function returns, and also signals better to the programmer that it's their responsibility for freeing any memory they allocate, and that my stircat is going to just use what it's given and do nothing surprising. So you'll see this approach being used in the system libraries all the time. Very common approach, and probably the one I suggest you use unless you do just want to play around with malloc. So that's our introduction to working with memory in C and solving these problems of how to return arrays and strings from functions. It takes a little more work than in other languages, but once you've got the hang of it, it should be reasonably straightforward. All right, so exercises. You're only going to learn enough C to have fun with if you actually have some fun with it. The first exercise I'm going to give you is FizzBuzz. You can do the classic FizzBuzz with all the printing out and stuff, but actually what I want you to do is to build up the FizzBuzz sequence in a string so you can test out all of the stuff with buffers and string operations. So that's exercise number 1. Second exercise is a prime sieve, which means you generate a list of prime numbers by eliminating all of the non-prime numbers. It's a pretty good one for working with arrays. After that, we've got another somewhat tricky string exercise, which is converting numbers into the word versions of those numbers. So instead of 74 as numerals, it would be 74 as words, and you can take that up to very high numbers. And then there's a final exercise for members as well. And did I mention this video is part of a project called Odes, which is about helping people to dig deeper into the field of computing and everything around it for people who perhaps haven't had the opportunity to do so yet in their courses or jobs. It's a YouTube channel where every video comes with a page with exercises and extra stuff to do in it. And the point of this is to get you from watching videos into doing this stuff yourself and really learning. So have a look at the website in the description. And if you want to sign up for a membership to support the project, I'd be very grateful. And here's where I'd usually touch my heart to show my gratitude, but I'm wearing a microphone, so that I think I just did it anyway. Anyway, so that's the end of the video. Hope you had fun. Do let me know how you get on with the exercises, and see you next time.